Hello, welcome everybody. This is the the Santa Clara Valley chapter of the Magnetic Society for the IEEE. We are a subset of the San Francisco and Santa Clara Valley IEEE sections. And we're hosting an event today for exploring the potentials of spin-orbitronics with Professor Manchon.
Thank you very much for this great opportunity. I really appreciate it. I know that it's probably everybody has had enough of Zoom meetings and conferences over the past 2 years, but so I really appreciate you being here today and giving me this opportunity. I understand that this community is rather oriented towards application devices and components. So not so much into, I would say, the deep device physics. So I'm a theoretician myself, and my job is to try to find and characterize fundamental mechanism that can be used to make devices. So we try to put as a few equations as possible and really focus on the effect and what we can do about them, how we can use them to create interesting components. So, I mean, of course, we're all here because of, thanks to the IEEE Society. So I'd like to really thank them very much for giving me this honor to be a distinguished lecturer. And I'd like to take this advantage of this presentation to just mention about the next Intermag 2023 conference that will take place in Sendai. So the broad topic, the broad field under which this spin-orbitronics takes place, it's called Spintronics. So Spintronics, is the manipulation of the spin of the electron. So this is probably something you're already quite familiar with. The typical device under which Spintronics takes place is this magnetic spin valve that is composed of two ferromagnets separated by a spacer. So typically the typical thickness here is of the order of a few nanometers, and this guy is typically 1 nanometer. This one here, the ferromagnets can be cobalt, iron, boron, nickel, nickel, iron, and so on. The spacer is typically copper or even a tunneling MgO barrier. And what happens is that depending on the relative orientation of those ferromagnets, the overall resistance of the device changes. So this is an effect that is called the gyromagnetoresistance, and that was discovered by Peter Grunberg and Albert Fert in 1980, sorry. So typically the way it works is that you have an unpolarized currents flowing through the systems, and of course the spin of the electron, which are the small magnetic moments of the electrons, are completely randomly distributed. When the current flows into the first ferromagnet, it basically gets polarized, and when it goes to the second ferromagnet, if the magnetizations are parallel to each other, then the current just flows without much scattering. There is scattering, but not too much. Now, if I actually switch the magnetization of the second layer, then what you see that the polarized current will actually meet a magnetization that is opposite to its magnetic moment. So you actually end up with a lot of scattering. Okay, it's not really a reflection, it's more like just a lot of scattering. So you end up with a high resistance, and this difference of resistance is called the gyromagnetoresistance. So that's this effect has been really revolutionary to it's been used for the design of magnetic relay heads, for example, or magnetic sensors. And I would say that was probably the first revolution of Spintronics. And the second revolution of Spintronics took place in the mid-90s when Luc Berger and John Suzuki predicted the actually opposite effect. So imagine that the two magnetizations are opposite to each other. So we are in the high resistance states. Now, if the current that you send through the system is high enough, is very large, then what's going to happen is that the second magnetization will actually get aligned on the polarization of the spin current. So you can manipulate the relative orientation of the two ferromagnets just by sending a current through the system. And this is known as the spin transfer torque. So these two topics have been studied in depth, and you actually have now applications based on those effects. The most famous one is, of course, the redhead of, the GMR sensor of magnetic hard drives. Okay, that really participated in the huge acceleration of the data storage industry that we have been witnessing recently. There is kind of a saturation in terms of areal density of information you can store in a magnetic disk. And now there are alternative technologies trying to use, for instance, a heat assisting magnetic recording to try to basically push the density of information further away. But I would say this is not really the topic of today's presentation. The second class of applications that is based on the spin transfer torque is the magnetic random access memory. So I believe this is probably something you've heard. So typically you take this magnetic spin valve I was mentioning, and the relative orientation of the two ferromagnets can be manipulated just by injecting a current through the system. So you can write a low resistance state and a high resistance state. You can basically, and the good thing is that if you turn off the current, then the magnetic state doesn't change. So it basically stays non-volatile. And this has been the basis of the magnetic random access memories. So that is the state of the art. That is actually what currently, well, researchers develop in the lab, and that where basically microelectronics majors are currently working on. So the field of Spintronics is wide. It actually covers many different areas. I just give you a very broad snapshot of what's going on. So one of the current direction is to exploit the spin-orbit coupling. This is the spin-orbitronics I'm actually talking about today. There's also a lot of excitation to manipulate anti-ferromagnet, which has, you know, those magnets, magnetic materials with no overall magnetization but a local magnetic order. There's also, of course, a lot of excitation about the topological materials in which the electrons behave as if they were relativistic particles. Or you have connection with superconductivity, which actually can be a very interesting direction, especially considering the current boost on quantum technologies. Spin electronics, where you use the heat gradient to manipulate spin currents. And of course, there's a lot of very intense research on ultra-fast dynamics, because, you know, the energy scale that is involved in spin precession in magnetic materials is typically of the milli-electron volt times energy scale, which means this corresponds to terahertz excitation. So that there's actually a very important area of research in this direction. And the last area I want to mention is magnonics, where instead of using metals or semiconductors, you actually use magnetic insulators. And the reason you would do that is because the excitation of the magnetic insulators are what we call magnons. They are quanta of excitations, of magnetic excitations. And those magnons can also carry spin information. So there's also a lot of excitation along this direction. So today's topic is just focusing on one branch of Spintronics, which is what we call spin-orbitronics. It's a bit of a weird name, so I'm going to explain a little bit what it means. But before I really enter in what spin-orbitronics is, I need to take a few steps back and explain something about magnetism. I believe that most of you are quite familiar with magnetism, and probably also with this experiment that is called the Einstein-Dehaas effect. This is also well known to be the only experiment that Einstein actually performed by himself. So the idea that you take a piece of paramagnet where the local magnetic moments are randomly oriented, and you magnetize it, you apply magnetic field so that all the magnetic moments align along the same direction. That's fine. I mean, to here, nothing crazy. Now, what happens is that during the process of the magnetization build-up, there is actually a mechanical torque that would be exerted by this magnetic orientation. And this Einstein-Dehaas effect really makes an equivalent between magnetic field and mechanical torque. You actually have the equivalent, I mean, the reciprocal, which is called the Barnett effect, where you take a paramagnet and now you actually make it turn over itself. And if you induce a rotation of this paramagnet over itself, the random spin will actually get magnetized. So you have then the reciprocal of the effect where the mechanical torque creates magnetization. And the reason I want to start with those two effects is because they really emphasize the angular momentum nature of magnetism. A magnetic moment is really an angular momentum. And that's what I want to talk about today. I want to try to exploit this angular momentum nature of the magnetic moment and see how we can use it to manipulate magnetization with currents in a much more efficient way. Okay, so let's actually look at how this angular momentum nature of magnetization impacts spin, can be used actually in the spin transfer torque context. So here is the idea. You actually take a metallic ferromagnet where, because it's a metal, it has two kinds of electrons, I would say, electrons contributing to the local magnetization and electrons contributing to the conduction. Okay, and those conduction electrons also carry a spin. And because there is magnetization in the system, the spin of the conduction electrons align on the magnetization and the local magnetization. Now, angular momentum conservation states that this number here must be a constant. So in other words, if you vary the spin of the conduction electron in time, there must be an automatic reciprocal variation of the magnetization as a function of time. So in other words, if I take a piece of magnet and I send a spin current through it, so let's send a current of spin polarized electron through my ferromagnet, you see that the polarization of those conduction electrons are misaligned with the magnetization, this big M here, of the local electrons. Now, when those conduction electron penetrates inside the ferromagnets, their spin progressively align on the magnetization of my ferromagnet. And when they get out of this volume, the spin current has a spin polarization that is different from the one it had when it was entering this volume. So you see that there is actually an imbalance in the spin orientation of the incoming current with respect to the outgoing current. So in other words, it means that some angular momentum has been deposited inside the ferromagnet. And as a consequence, this induces a torque on the magnetization. So this is really the essence of spin transfer torque, okay? So there is not much spin-orbit coupling at this stage. I will actually come to spin-orbit coupling a bit later. Now, what can we do with the spin transfer torque? So exactly this effect I was mentioning is this current-driven magnetization manipulation. If you want to understand what's happening, you can just look at the famous Landau-Lipschitz-Gilbert equation, which govern the dynamic of the magnetization of the free layer here. Usually we have three components. So very quickly, this is the magnetization. The effective field here is given by the anisotropy and the external field. So if I just say that this is where the effective field is, then the first terms induces the magnetization to precess around the easy axis. Now you see I have another term here, which is the damping term. So this one removes energy from the system. So if I just have those two terms, the magnetization will start precessing and progressively align along the easy axis. That's fine. Now, the spin transfer torque, the torque I was mentioning, that was discovered by Luc Berger and John Suzuki, is this last term here. The P here is the polarization of the incoming current. M is the magnetization of the free layer. Now you see that if you look at the geometry, this torque, so if I just take the polarization on the easy axis also, like typically in this situation here, the torque must be actually aligned or anti-aligned on the damping torque. Okay, that's why we call this guy an anti-damping torque. So keep that in mind because we're gonna come back to that later. So depending on the sign of this coefficient here, so this coefficient is just proportional to the current that you send through the structure. Depending on the sign and on the magnitude, you can have different regimes. So if the torque here is much smaller than the damping, in this case, of course, the magnetization relaxes toward the easy axis. Nothing really interesting here. Now, if the torque is much larger, you can completely reverse the magnetization. So you can switch the magnetization with the current. Then finally, if the torque exactly compensates the damping, you basically continuously bring energy to the system so that the damping is compensated. And in this case, you can induce self-sustained magnetic precession. And because this precession is on the gigahertz range, you end up with a gigahertz, well, basically radio frequency generator. So this kind of switching and excitation has been observed in the typically in 2000, I mean 1999 to be precise. And yes, it's actually now one of the most important topics of Spintronics. And as I mentioned, you can use it now in devices and make magnetic random access memories out of it. So here are just a couple of structures, the typical spin valve that people use to perform current-driven magnetization switching and oscillation. And what you see that these are very complex structures. So here, if you just take this one here, the cobalt iron boron is a magnet. You have some tantalum here that will induce some antiferromagnetic coupling. The MgO barrier give you the tunneling barrier, and the two important layers are this guy and this guy. These are the active layers. All the other layers here are meant to stabilize the magnetization direction for the growth, to control the growth of those multi-layers. This one is a bit simpler, but you see you have some antiferromagnets here. So all those layers are just meant to stabilize the three important active layers, the polarizer and the free, the polarizer here and the free layer. So free layer, polarizer, I'm sorry. So you see, it's actually a very complex structure, and these are just some of the stack that people use in, that industry are developing. And as I mentioned, these stacks are used to create to generate magnetic random access memories as well as radio frequency oscillators. Now the question is, can we get rid of the polarizer? So again, look at this structure here. What if you can find a way to only manipulate this layer without the need for, this layer here, without the need for all the other layers here? So in this case, I would just I want to find a way to manipulate this the magnetization of this layer without having all this complex stack below to stabilize the polarization, the polarizer. So there is actually a way. So the reason we need a polarizer is because we need to take the angular momentum from somewhere. We need to create a spin current in the first place. Now, what if we find a way to circumvent the creation of the spin current and we completely can get rid of the polarizer? And that's actually the topic of this presentation. We can do that by exploiting spin-orbit coupling. So the way you can understand that, so I will try to avoid to put too many equations and really try to give you some hands-waving feeling of what's happening here. So if you ask Einstein how he does, if he wants to, when he's riding his bike, and if you want to turn left, well, he will probably answer you that if you want to create an angular momentum that makes the bike turn left, you actually have to, of course, rotate the wheel. So you actually have to create this angular momentum here. But the problem is that, well, just for mechanical purposes, you also have to create another angular momentum here. So you have to bend left if you want to turn left. And if you want to turn right, you have to bend right. Rightward, sorry. So essentially, you want to create an angular momentum, you have to take it from somewhere. And that's what spin-orbit coupling is doing. So we're going to concentrate on two main effects in this presentation. The first one is the spin Hall effect. And the second one is has a very strange name. This is called the inverse spin galvanic effect. I'm just going to come back to it in a minute. So what is the spin Hall effect? I'm pretty sure you're all familiar, at least in your everyday experience, about Magnus force. So Magnus force is this force, this transverse force that applies on a rotating ball when it flows and let's say moves in a fluid. So of course, while this is a very famous and very painful, I have to say, very painful memory from the 1997 World Cup selection when Brazil scored against France. So this is a French ball here, and the way Roberto Carlos did is that he actually made the ball spin so fast that the ball went around the wall. It really had this very strangely curved trajectory and went inside the goal. And to do that, you actually make the ball rotate so fast that, you know, the flow of air on each side of the ball is different, so that the relative speed of the air with respect to the ball is actually much higher at the bottom than at the top here. So this creates a difference of pressure, which creates a Magnus force that pushes the ball and bends its trajectory. Now we have the same thing in condensed matter. If you send a current of electrons, we know that electrons possesses two spin, right? Spin up or spin down. So essentially two intrinsic rotational degree of freedom. And what's going to happen is that spin rotating one way will tend to bend in one direction, while spin rotating the other way will tend to bend in the opposite direction. So you send an unpolarized charge current to your system, and you're going to create a pure transverse spin current. So you see, I don't need a polarizer, and I still end up with a spin current. And for a long time, these effects were thought to be very, very small. Actually, the first experiments on spin Hall effect observed efficiency of the order of 0.001%. So something completely ridiculous if you compare that to the polarization of cobalt iron boron, which is typically 90%. So there is actually another effect that also I want to mention, because that's crucial in the structure I'm going to talk about. It has a very weird name. It is the inverse spin-galvanic effect. I mean, sometimes it's called the Edelstein effect, the Rashba-Edelstein effect. I prefer inverse spin-galvanic effect, but that's just personal taste. And the idea is the following. What if you want to avoid to bend the trajectory? What if you want to make sure the trajectory is straight, is a straight line that doesn't curve? Well, in this case, if you have Tom Brady, will probably tell you, okay, you just have to place your hands on the ball in such a way that you induce a rotation of the ball that is along the trajectory. And if you do that, you actually stabilize the trajectory of your ball. So you have, if there are hunters in the audience, you actually are pretty familiar with that. You have this riffling in the barrel of a gun that would do exactly the same thing. That would induce a rotation of the bullet along the trajectories to stabilize it. So in condensed matter, you have the same effect. Now you remember you have two spins. So whether the fact that spins can be either along or aligned or anti-aligned to the trajectory is exactly equivalent. So if you want to make sure that you end up with an effective polarization, then you need to break inversion symmetry. That's something I will be very fast. And of course I could talk more about that, but so you basically have two effects: spin Hall effect and inverse spin-galvanic effect. The latter only working when you have inversion symmetry breaking. So typically an interface. Okay, so now with those two effects, what can we do, and how can we use that to manipulate magnetization? So I'm going to focus on a very simple system, much simpler than this multi-layer I was showing previously. I'm going to take a ferromagnet, deposit it on the top of a heavy metal. So here my heavy metal is platinum, and the magnet is cobalt nickel. This is just a cobalt nickel multi-layer, which enables the magnetization to lie perpendicular to the plane. That just, I would say, a technical detail. It's not that important for the physics I want to mention. Now, what you see that at this interface here, I have inversion symmetry breaking. So what I'm expecting is that I should have spin Hall effect inside platinum. So if I send a current here, I'm going to generate some spin Hall effect. And right at the interface, I should have inverse spin-galvanic effect. So I'm going to have those two effects together in this multi-layer. Now, right at this interface, what I should have is that if I send a current through the system, I'm going to generate some spin density right at this interface. This spin density will be absorbed into the ferromagnet, and I will create a torque. So it's a variant of the spin transfer torque I was mentioning, except that here I do not have a polarizer. There is actually another effect that is really a parent effect of the spin-orbit torque, which is called the Dzyaloshinskii-Morita interaction. So the way it works is that right at the interface between a heavy metal and a ferromagnet, I can actually stabilize chiral structures. So it's a bit strange, but this is, I don't know if you guys have heard about magnetic skyrmions. So magnetic skyrmions are magnetic objects with a certain chirality So typically, textures where the magnetization will create some vortices, for instance. And in fact, this interaction is very, very important because it's ubiquitous. Each time you have an interface with magnetization on one side and heavy metal on the other side, you're going to have both effects. So spin orbit torque and some Dzyaloshinskii-Morita interaction that creates chiral magnetic structures. And both of them are very important to consider. So let me summarize. So if I take my bilayer here, I take my bilayer, I send a current through my bilayer. So this is my heavy metal, this is my ferromagnet. In my heavy metal, I'm going to have a spin Hall effect. Okay, spin Hall effect is a separation of up and down spin so that my ferromagnet will absorb a spin current without a polarizer. No need for that. And the torque I'm going to get out of it has this particular form here. This is the magnetization. The Z is the normal to the interface, and E is the electric field I'm applying to the system. This particular form looks very much similar to the torque I was mentioning previously. It actually has very similar physical origin. And this is called a damping torque. So this one can switch the magnetization. Now, right at this interface, I have this inverse spin galvanic effect. So it's a bit technical here. You don't need to enter into too much details. What's going to happen is that I will send a current and I will create a spin density right at this interface. This spin density will actually act like a field on the magnetization. It's exactly like if I apply a magnetic field, like an Ørsted field, if you wish. It's a very localized Ørsted field, localized at the interface between the ferromagnets and the heavy metal. So I'm going to end up with a torque that basically looks like a field-like torque. And finally, as I said, right at this interface here, I should have the Dzyaloshinskii-Morita interaction that will create magnetic skyrmion. So this is the Lorentz TEM image of this magnetic skyrmion, and this is in bulk manganese silicon. You can also get them in multi-layers that have inversion symmetry breaking. So here I think you have iridium, platinum, ferromagnet, iridium, platinum. So there is inversion symmetry breaking. And you end up with those skyrmions, which are isolated here, metastable skyrmions, in fact. And this is the form of the Dzyaloshinskii-Morita interaction. I don't want to spend too much time on the math. I really want to focus on the phenomenology. And I will explain in a few minutes how this interaction impacts the magnetization dynamics. So of course, I'm a theoretician, so it's very hard for me not to show you any formula, equation, or some calculation. So my job is to better understand those effects, spin-orbit torque and Dzyaloshinskii-Morita interaction. So the kind of calculation we can do is you have developed some time-bending model of a slab structure where we have a non-magnetic metals on a ferromagnet. Just bear with all these details here. We can use some parameterization to extract a band structure that is as close as possible or as reasonably close as possible to a real-life system. And we can actually track the spatial profile of the spin density in our system. So this is just to demonstrate a little bit what we've been doing for the past 10, 15 years to try to better understand the physics of the spin orbit torque. So here is the configuration. The magnetization is perpendicular to the plane. This is my bilayer. I mean, here I just represent the ferromagnet, but you can imagine that there's a heavy metal right below. I send a current through the system and I'm going to record the spin density Sy, Sx, to the spin density that is perpendicular to the magnetization that is induced by the current. So this is the profile. Just look at the red, the black line here. You see that the Sy component, it's actually the one that is giving you the field-like torque, is really localized at the interface and not much present in the heavy metals. If it's a heavy metal, this is a ferromagnet, heavy metal ferromagnet. Well, the Sx component, which gives you the damping torque, is much, it's actually broadly or smoothly decays within the ferromagnet. So we can attribute some very nice physical mechanism behind that. So the Sy component here, which gives you the rise to the field-like torque, is in fact really attributed to the interfacial Rashba effect. While the Sy component, in fact, is a bit more complex because you do have some spin Hall effect, but you also have some very important interfacial contribution that is coming from some very curvature, some very fancy theory denominations. So typically what we do in this calculation that we vary we vary the thickness of the heavy metal, and we record the torque as a function of the thickness of the heavy metal. And what you can see that the torque, the field-like torque, is completely flat as a function of the thickness, while the damping torque changes sign and is not flat at all. So this really characterizes an interfacial effect, while this characterizes a interfacial plus bulk effect. Anyway, that's a bit technical here. What we've also been doing on the Dzyaloshinskii-Morita side was to try to understand the role of materials on orbital hybridization. So typically, if you want to maximize or to reduce the Dzyaloshinskii-Morita interaction at interfaces, what kind of materials should you use? What kind of guidelines can you establish? So we have been performing some density functional theory calculation. So it's actually a very fancy and advanced approach that was developed by Stefan Blöger's group in Germany, in Jülich. So what we do is that we actually create a spin spiral in momentum space, projected in the spin-orbit coupling, Hamiltonian, and we can extract the Dzyaloshinskii-Morita interaction. What is important here is that we have been doing that. Actually, he has been doing that. Belabes, who has been really the spearheading all this work. He has been doing this calculation on many different systems. So a bilayer composed of 5 different 3D metals, so chromium, manganese, iron, cobalt, nickel, deposited on different substrates. So some of them are realistic substrates like tungsten, platinum, gold, iridium. Of course, osmium and radium are a bit more, I would say, academic. But the good thing is that we can have a global behavior. And what this investigation points out is that there is a need for a very specific compromise between 5D electrons and 3D electrons. So that has a direct consequence when you design a system. You have to choose the materials properly in a very smart manner to maximize or minimize the Dzyaloshinskii-Morita interaction. So I'm just going to take 2 points. If you just take this this point here, the gray zone where you have the maximal Dzyaloshinskii-Morita interaction, and I'm just going to take this point and this point. So the manganese tungsten and manganese gold. I'm sorry, not gold yet. Sorry, manganese tungsten, and I'm taking this point here, nickel tungsten. Okay, so you see that manganese tungsten has a large Dzyaloshinskii-Morita, nickel tungsten has a very small one. And if we look at the density of states, you see that the manganese density of states is very small. It's non-zero. That's very important, but it's very small at Fermi level. And actually, what dominates the density of states are the 5D electrons of tungsten, which is fine because tungsten has a strong spin-orbit coupling, so you end up with a strong Dzyaloshinskii-Morita. Now, if you take nickel, what you see that nickel has a lot of 3D electrons, so the proportion of 3D electrons is much larger, and 3D electrons have a small Dzyaloshinskii-Morita, a small spin-orbit coupling, so you end up with a small Dzyaloshinskii-Morita. Now, if you look at gold has a strong spin-orbit coupling, but in this particular case, actually, what is interesting that the 5D electrons of gold are very far from the Fermi level. So all the spin-orbit coupling you can get is from the 3D materials, which are much lighter, in fact, than the 5D. So you end up with a small Dzyaloshinskii-Morita. Anyway, that was just to show you what can be done from a first principle calculation. So you can really design systems or suggest materials for optimize device performance. Okay, that's the bit of anyway. So there's a charge transfer. There's a lot of very nice physics behind it. Now, what I would like to do before I move to the next part of my presentation is to pinpoint an important issue that people have been facing in the experiments. So the prediction of the spin-orbit torque has been published between, I would say, probably the first paper was in 2009, our own was in 2008, and there was another one from Alan MacDonald and Garate in 2009. So typically between 2005 and 2009, you had like 3 or 4 theory papers predicting the effect to occur. And a couple of years later, within a couple of years, 2 groups, one in Cornell in the US and one in Spintech in France, actually demonstrated that you can indeed manipulate the magnetization just by injecting a current. And I have to say that Barcelona was also involved. I apologize for forgetting Barcelona. So the way it works is that you have this, let's say, platinum and cobalt. If cobalt is very thin, then cobalt magnetization will be perpendicular. You send a current through the system, and as I said, you should have a spin Hall effect and Rashba effect, all this business happening. Now, if the magnetization of cobalt is homogeneous, what's going to happen is that the torque due to the spin Hall effect will bring the magnetization in the plane. And if you don't do anything else, you're screwed and you cannot do much, because you see that once this is in the plane, when you turn off the current, the magnetization can either go back to its original position or switch down. Okay, it's not going to stay in the plane because it's not a good, it's a hard axis of anisotropy. Now the premise that you want to make sure that you can systematically switch the magnetization. So what you need to do is to add a magnetic field that will kick the magnetization out of plane in the right direction and switch it completely in a systematic manner. Now that is a scenario that happens for homogeneous magnetization, and in fact, this is not quite what is happening. What people observe is that you actually have domain walls in the system. The reason is because you have a perpendicular magnetization and domain walls are very, very small. So even if you have small devices, there's a very good chance you're going to have magnetic domain walls. So the blue region here means magnetization down, red means magnetization up, and in between you have a smooth variation of the magnetization from one domain to the other. And what is actually happening is that when you send a current through the system, you are manipulating the domain walls. You are moving those domain walls. So you're probably familiar with the racetrack memory that was proposed by Stuart Parking. And that's typically the kind of idea that is behind it. You want to manipulate the domains here. And this is an experimental image that was taken by Dan Ralph's group in Cornell, where you can see that this is in fact the current-driven switching of this kind of bilayer. And you can see that there is a very clear domain wall motion here. So the switching is not a coherent switching, it's a complex switching. Now, what is happening? So if there is no specific, I would say, if dipolar energy dominates the domain wall energy, then the magnetization inside the domain wall should be along the transverse direction here. So you see this magnetization here should be aligned along the polarization of the spin Hall current, okay, the current that you're injecting from the platinum. So well, the torque will not do anything on those domains here, and you will end up with a kind of a coherent switching of each of the domain. Now, the problem is that this is not quite what is happening. In fact, people have observed that because of the Dzyaloshinskii-Morita interaction, okay, that's where this one is becoming important. In fact, the magnetic moment inside the domain wall is not in the, this one is called the block configuration. It's actually in the, what is called the nail configuration. Okay, you actually have this, the magnetization is actually perpendicular to the domain wall direction. And most importantly, it has a certain chirality. Okay, it has a certain direction. If I switch the sign of the Dzyaloshinskii-Morita, let's say I put the platinum on top of the system, then the spin here, the magnetic moment here, we switch direction, and this one will also switch direction. Okay, that's why there is a chirality. There is just one way the magnetization turns around the transverse direction here. Now, if I send my current and I induce a spin Hall effect, well, the spin Hall effect will actually make all those domain walls move in the same direction. I'm not giving you any math, any mathematical equations behind it. I mean, unfortunately, you have to trust me, but that's what would happen. So if you do not apply a magnetic field, then all those domains move. That's fine. It's actually useful for the racetrack memory. The problem is that if you want to switch, you want to expand the domain and shrink one domain. Okay, and this is not what is happening. All the domains keep the same size. They just move together. Now, if you want to break that, you need to apply a magnetic field. Then all the magnetization will switch. The magnetization inside the domain wall will switch along the same direction, and then the red domain will shrink, while the blue domain will expand, and then you can get a switching. The reason why this complex mechanism is so important is because the domain worlds are moving so fast. We are talking about kilometers per second. So this, very specific dynamics, it's very specific to this kind of system. You can actually induce picosecond-like switching. So it's very, very useful and interesting for ultra-fast magnetic memories. Now, the problem is that I need this magnetic field. So there have been some strategies to try to avoid applying magnetic field by engineering the structure. I'm not going to talk about that today. What I'm going to talk about is, okay, can we actually engineer the crystallinity of the system? Can you actually choose, smartly choose material with specific symmetries and induce an effect and basically get rid of this magnetic field? Because if you want a magnetic field in your experiment, you need to have an apparatus to generate it. It's a very non-local effect. It's basically terrible. You just want to get rid of that. Okay, so can we get rid of the magnetic field? So, so just a very short advertisement about spin-orbit torque before I move on. So you can use spin-orbit torque to manipulate pretty much everything. So magnetic metals, as I just mentioned, also magnetic insulators, in fact, non-central symmetric materials, anti-ferromagnet. Unfortunately, I won't have time to discuss about that today. And you can imagine many classes of devices out of that. So I really encourage you guys to have a look at those at this manuscript, which was written by a wide range of experts in the field. We try to give a broad perspective of what's going on in this exciting domain. So let me take the last 5 minutes to talk about what happens when you break more symmetries in the system. Okay, up to now, I only talked about bilayers when you have a ferromagnet and a heavy metal, and I didn't talk about crystal symmetry. So what happens if I try to take into account crystal symmetry, and what happens when I break mirror symmetries or rotation symmetry? So what you know probably from from basic physical principles is that if you look at the response tensor, it could be strain, it could be conductivity, anything, even spin torque. The response tensor of a system that has specific crystallographic symmetries should have at least the same symmetries as the crystal that you are working on. Okay, so there's a mathematical formula that would basically constrain the tensor with the help of the symmetry operation that described the crystal. And there was actually a couple of heroic work by Jakub Dzyaloshinskii and Mr. Wimmer to try to constrain the tensor of the spin-orbit torque in different crystals. So here we have all possible crystals. Today I'm going to talk about one specific crystal that was studied by my good colleague in NUS. So yeah, I will probably just focus on one particular experiment. I mean, there have been previous experiments on manganese nickel antimony, for example, where in principle you are supposed to have this Dresselhaus-like symmetry of the spin-orbit torque, and we actually end up with something that is a bit more complex. There have been some very nice work by Dan Ralph's group in Cornell, also by my colleague Shishang Zhang in Saudi Arabia on this tungsten ditelluride, but I don't want to talk too much about that. I really want to focus on the recent experiments performed by Jingsheng Cheng in NUS. So he's also an IEEE Distinguished Lecturer, so I really encourage you to invite him if you haven't done so. He's an expert in growing perpendicular materials. And what he did recently was he considered this bilayer between copper platinum and cobalt platinum, copper cobalt. So this is a non-magnetic system. This is a magnetic system. And what is interesting is that he actually grew them in the L11 phase. So what is this L11 phase? It's a very well-ordered phase. What is interesting is that if you look, if I just cut, it's along the 111 direction. So if I cut along the 111 plane, you see that these gray atoms here are the platinum, and the yellow, the red spheres here are either cobalt or copper. What you can see that there is a mirror symmetry in this direction, but no mirror symmetry along this direction. And there is a threefold rotation. Now, the question is, what do you observe in this particular system? And what really surprised him is that he basically took this bilayer, and they inject the current in this bilayer to try to induce current-driven switching. Okay, exactly the same thing I was mentioning. Now, what was very surprising is that he could get a switching independent of the magnetic field, so it doesn't need to apply magnetic field. That was a bit surprising. But most importantly, depending on the direction of the current with respect to the symmetry axis, you actually get very different forms of switching. So if you apply the current along low symmetry direction, you know, this perpendicular to the mirror typically, then you get a nice switching hysteresis. Okay, you can switch from up to down. That's fine without magnetic field. So that's actually a very interesting aspect. Now, if he applies along the high symmetry direction, let's say 30 degree, doesn't get any switching. If he applies along another low symmetry direction, but at 60 degree from the original direction, you get the switching, but in the opposite direction. Okay, it goes from down to up and not from up to down, and so on, so on, so. So he actually has an oscillating behavior depending on the crystallographic axis. So we try to understand where this thing was coming from. And so we apply this group theory that I mentioned previously. And what we get was this form of the torque. So this first here is the feedback torque. That's easy. This is the spin Hall effect that gives you damping torque, easy peasy. Now, what is interesting, the last torque here, well, that has a very surprising form, very, very, very different from everything we knew. And actually, this torque is doing all the interesting jobs. So let me try to explain you, and then I will stop on that. So we take this configuration here. I send a current along one particular direction. Let's say this is the one of the high symmetry direction of my system. So the damping torque, the torque coming from the spin Hall effect, we bring the magnetization in the plane. Okay, so I just bring in the plane. Now, when the magnetization is in the plane, then this one turns on. Okay, that's a very important point. This torque is completely irrelevant when the magnetization is perpendicular. It's only active when the magnetization is in plane. And when it is in plane, you see that depending on the direction of the magnetization on the electric field, this form here can be either, let's say, through the up direction. So this one basically brings the magnetization back to its original position, so no switching. If I send a current along the, let's say 30 degrees, and the magnetization goes in this direction, and I can calculate that this torque actually goes to 0. So again, no switching. That's interesting. But now if I send the electric field along 60 degree, then you see that I just manipulate the torque, I just plug in all the parameters, and I end up with a torque that is in the right direction, and then I get a switching. So that was actually the interpretation for this field-free switching that you can do with this perpendicular magnetized sample with very high, highly interesting symmetry. We have actually done that also on the Dzyaloshinskii-Morita interaction, but we stop here. Probably for those who are familiar with the magnetic two-dimensional materials, so there have been a lot of excitement in the past 5 years. People have been producing magnetic materials in 2 dimensions. And one of them was, some experiment claimed to see magnetic skyrmions in some of those materials. And that was very surprising for us because again of symmetry. Symmetry should actually cancel Dzyaloshinskii-Morita. So we have been performing, sorry, I have to put some equations here. We have been performing some symmetry analysis and most importantly, some calculations. Let me spare you on the calculation. What our conclusion was is that in this particular kind of 2-dimensional iron germanium tellurium magnets, you can actually stabilize in plane spin spiral, but only along low symmetry directions here. You can see that, this direction has a low symmetry because if you go from this magnetic atom to the other one, you can either go this way or this way. These are inequivalent paths, and that creates a Dzyaloshinskii-Morita. So very different from the interfacial Dzyaloshinskii-Morita I was mentioning. So if you want to learn more about Spintronics, I'd like to encourage you to have a look at my channel on YouTube. I have a series of lectures on magnetism and Spintronics. I would like to thank very warmly my collaborators back in Saudi Arabia when I was there. Now I just moved to France 2 years ago. So I'm building a new group here in Marseille. And I would like to thank very, very deeply all my collaborators. theorists and experimentalists who have really fed me with a lot of ideas and motivation over the past 10 to 15 years. So thank you very much for your attention.
Thank you very much for sparing us some of the math in there and getting to application and into the theory, for coming and volunteering your time.